Welcome. We are going to begin transitioning into our final module of the course where we look at a class of non-polynomial functions, and in general they're going to be called exponential functions and logarithmic functions. You may have seen them before, maybe you haven't. But either way, as we begin the transition, we want to kind of switch our thinking about how we think about change and how the math of change is affected. Typically, when we look at polynomial models, there's some sort of predictive behavior between change. Mainly in linear functions, we said that there was a constant change, like y equals mx plus b. We were always changing by m. Now, that constant change isn't going to happen necessarily. So let's look at an example. Okay, so we're looking at a colony of bacteria, and we're tracking its population each day for 10 days. And the data is below. We want to determine a model for the population of bacteria at day t since the experiment has started. Okay, so the data table is here, right? And as I just begin a preliminary investigation of the information here, I see that as I go down the table in t, right, I'm always adding 1 until the last one where I'm adding 6, right? So I forgot to record data from days 5 through 9, whatever, it's fine, we have it there. And then as we go from here, we would do, we'd see, okay, population increases by 1,000, right? Population is in thousands. And then 2,000, and then 4,000, and then 8,000, and then a lot, okay? We can figure out the math later, 10,008. But anywho, the idea is that if we had a linear model, y equals mx plus x plus b, right? In this model, this is when we had constant rate of change. Constant rate of change. And we said that the rate of change in this scenario was equal to m. As we increased t, and again, this would be change in y over change in x. So if we changed x by 1, our y change, or our dependent variable, our output, would change by whatever m was. Well, in this case, as we look at p, right, it doesn't change by the same amount each time. It's variable. Okay, and we could look at a second difference here too. So like take the difference of the differences. So that's plus 1. That's plus 2, this is plus 4, and you can continue to investigate it, like you can do differences of the differences of the differences, so the third differences, and you're going to get the same sort of pattern, 1 and then 2, and then this 1, 2, 4, 8 pattern is just going to continue popping up. Okay, when we see those differences, no matter how many times we do them, be variable, that means we can no longer use a polynomial function. Typically, if we can just see that the differences, are constant at some point, that tells us a bit about the degree of the polynomial we might be working with, okay? But in this case, I'm going to say we have non-constant rate of change. And there's actually going to be a different word I'm going to use instead of non-constant, but we'll just say non-constant for now. And then the question is, what's our function, what's our model, mathematical model, or algebraic representation in this situation, right? That's what we want to know more about, okay? We'll come to call these exponential functions in a moment, but in this case, as I look at the function here, instead of looking at additive behavior, what I'm adding each time, I can actually look at this a little differently. Let's erase all these, okay? I notice that in going from 1 to 2, I multiply by 2. And going from 2 to 4, I multiply by 2. And going from 4 to 8, I multiply by 2. And again, I keep multiplying by 2. And then here, I'd probably multiply by 2, 6 times? So like 2 to the 6th. Okay, I could check that and verify, but it actually does end up working. Okay. And what I notice is that instead of being additive, I have multiplicative. Okay, so what I would see is that to get, say, the next entry in the table, so this is what I have next, this is the next value for the input, I would take the current, okay, so this is the current x value that I have, and I would multiply by, I don't know, let's call this b, okay? So, in other words, what I would see here is if I look at, say, p of 2, I would take p of 1 and multiply by 2. My b value would be just what I multiply by, so p of 2. So this is, just to be clear, this is 1 times 2, and then p of 2 is 2. Does that work out? Yes, it does. Okay, so when this behavior happens, this is an example of a non-constant rate of change. Otherwise, I'm going to say it's constant proportional. Okay, proportional means that things can be related to one another through a constant. Similarly, you could say, if you look at what you have next over what you have now, that would just be your constant, and this is your proportionality constant. Okay, proportionality constant. Constant. Okay, so when you have a constant proportional rate of change behavior going on, that's when you're going to have what we're going to come to call exponential model. Okay, also one of our first classes of a non-polynomial model. So we'll get into more details in a minute, but as you encounter situations where you can't continually add and you look at the differences and those differences don't make sense, that's when you need to turn your eye towards exponential models as a first type of non-polynomial function to examine first. And in those situations, look for that constant proportional behavior. Are you always multiplying by something? If so, an exponential model may be just the function that you need.